When we looked at the reduction, we talked about these two, going from an acyl chloride to the aldehyde, or from an ester to an aldehyde. Right, we said the acyl chloride to the aldehyde at least made sense, because this is going down in reactivity. The ester upwards, or the ester to the aldehyde, doesn't make sense because we're going up in reactivity, right? So yeah, they're a bit odd in that respect, but these are reactions that we can go through and do. We end up with two different sets of reagents. We've got a lithium aluminum hydride reagent, or we have another lithium aluminum hydride reagent over here. Okay. The bottom one is more commonly referred to as DIBALH, or actually just DIBAL, or dibal. Okay. It's diisobutyl aluminum hydride. So our textbook's being nicer because they're including the H for the hydride part of it. But we have our isobutyl. So diisobutyl aluminum hydride. Okay, so we still have that aluminum hydride bond, so we can get rid of that hydride. What are some common features that we see within these two reactions? Why, yes, I agree. We have OT-butoxide and the isobutyl. Both of those groups are sterically very large. So we have a large steric control behind our reagents. What are you going to suggest, Jenna? You were going to suggest the steric control, and that's why you're now silent, because I took your thunder. Oh, okay. What other similarities do we see between these? Or is that it? Very, very, very cold. Okay? So that steric control is going to limit the reactivity, and the cold will do what? Favor the kinetic, meaning that it is limiting reactivity. Right? So both of those conditions help to support and limit the reactivity of these. Okay? These just happen to be the two kind of more famous of our hydride sources used for reducing our carbonyls or reducing our acid chlorides. There are tons of others. And as we talked about on Monday, a lot of those are derivations on what are the substituents. Okay, here we use T-butoxide or isobutyl. Okay, we can make them phenyl rings. Each of those kind of modifications changes how the reagent reacts and minimizes how it can react and with what it can react. Okay, so we just kind of have to look for that. The biggest thing that you need to get out of it, regardless of the source, is at the bottom. Look for that metal hydrogen bond. Okay. If you find a metal hydrogen bond, what should you be seeing? You should be seeing H minus. H minus can now be used as a nucleophile. Okay. Yes, there are exceptions to that, namely sodium hydride, which acts as a base. But if we think back to all of our hydride situations, really there's only the one exception. Okay, hydride. Pretty much everything else went through and did some kind of nucleophilic attack. Okay? So both are bulky and both run cold. Okay? Yeah, that's pretty much what you need to remember for those. Make sense? Okay. So what we'll then move into is our organometallics, because that gets us what kind of a nucleophile? We get a carbon nucleophile. Okay? Because we have these carbonyls, okay, or acid carbonyls, we have a really good electrophile. So we want to run all of those reactions we ran in the previous two chapters. again, but now with the acid derivatives, because we can have that leaving group ability, okay, or see how that leaving group can affect our results. So we'll go through and run our negative carbons. What are our negative carbon sources? Grignard. Gilman. Wittig. Wittig is a special case. Why is it a special case? It's going to create an alkene. It's also only going to go with our aldehydes and ketones. The what? Alkyl lithium? Okay. Our alkyl lithium, which could then be reacted with copper to make our Gilman reagents. So the Gilman are sometimes known as your organocuprates, which comes from an alkyl lithium structure. Okay. Acetylide, cyanide, enolates. Okay. All of those are potential carbon sources for nucleophilic attack. Okay. So the next sequence is pretty much now what happens when those reagents react. Okay. So if we look at the big ones, our organolithium, or our alkyl lithium, Grignard, and then our cuprates, also known as our Gilman. Is there any kind of line that you might draw between those to be like, these ones react the same, these ones react different? Yeah? What's that line?
I would say right under the Grignard.
Yeah, right under the Grignard, we get a big difference between the Grignard and our Gilman. That difference manifested in what? Where do we see that difference show up? That was our alpha beta unsaturated carbonyls. Everything above that line did a 1,2 addition. And below that line we did a 1,4. Right? Why did we do a 1,4 instead of a 1,2? Or 1,2 versus 1,4? True, we could label them also as kinetic and thermodynamic, but why did we see that difference?
The lithium and the Grignard were stronger. The carbon nucleophile was stronger.
The strength of the nucleophile. Your Grignard and your alkyl lithiums were those stupid strong nucleophiles, and the cuprate turned out to be just a strong nucleophile. And that was kind of our arbitrary line between those. Okay? Why might that be relevant if we drop down to our acid derivatives? If we take a look at our acid derivative, we can do our nucleophilic addition. Can't believe I'm going to do this, but I'm going to draw it. Followed by our nucleophilic elimination. Right, to produce that product. Good? What is the issue with that product? Or what do you see in that product? The red one. The now red one. I'm not asking does it look wrong or valid or any of that. I'm asking what is in it? What do you see in it? Carbonyl. What do you see in your starting material? Carbonyl. What happened when we had a Grignard reagent and a carbonyl in the previous section? We have an electrophilic carbon. What did the Grignard do? It attacked it. So if we have a situation where we're running with the Grignard, more than likely what's going to happen is we're going to get 2 additions. Whoops. We will only get 1 nucleophilic elimination. Why only 1? Couldn't those electrons come back down? Yeah. What would they have to do if they came back down? Kick something out. That something would have to be a carbon, which is a bad leaving group. Can those electrons come back down? No. Right? So we would get a nucleophilic addition followed by an elimination followed by a nucleophilic addition. So we're adding on to our pieces. Okay? That reaction is all because we have a strong nucleophile. Why might that be important? Particularly when considering the list right above. Are all of our carbon nucleophiles the same nucleophilic strength? No. We might expect a difference between how far our nucleophilic attacks go. Okay? The Gilman stalls at the single carbonyl. Okay? It's not quite nucleophilic enough to do that direct attack, so that if I wanted to stop at the ketone, I could use the Gilman. Okay? If I wanted to carry through, get all the way down to the alcohol, eventually, that's where I would use the other reagents. Okay? So that kind of modulation in reactivity that was addressed back when we looked at our carbon nucleophiles in the nucleophilic addition also shows up in the nucleophilic addition and elimination sections. Kind of make sense? Okay. So there's our kind of standard mechanism, our nucleophilic addition, elimination, addition, and then we'd almost always have to follow that up with a proton transfer. That proton transfer isn't always shown in your reagents. It should be, but that doesn't mean it is. Okay? So kind of watch out for that. I will always try and make sure I include it as a secondary step. Clearly did a piss job of that because it's not there. Okay? And that one's actually mine, so that is my fault. So take a look at some products. What do you think we're going to get? And so, ta-da, were you right? Questions on that? You all got it? Cool. Awesome. So no questions about it? Did you have a question? Yeah.
So does the OCH3 leave?
Yep, so that's an interesting question. Why would the OCH3 leave? Okay, once we did our nucleophilic attack, we have O minus, we have OCH3. It's just a methyl, that one, right? Yeah. CH3. We could have those electrons come back down, and then it would kick out OCH3, right? And then we'd have to do through a couple more steps, but one of your side products would be a negative oxygen. Well, is that negative oxygen a good leaving group? No, you're saying it's an awful leaving group, so why is it allowed to leave? What we're doing is comparing across the reactant to product in that first step, okay, or sequence of, actually even the first step. We have a negative carbon and we end with a negative oxygen. Negative oxygen in that next step resulting in a negative oxygen. All of that's fair game. There's no kind of transition there that makes that bad. As an added bonus, once the OCH3 leaves, we would end up with, I'm going to have to draw it up at the top, a structure with a carbonyl. What is special about that carbonyl? Resonance. Okay. So I can stabilize that negative charge better than I can the negative oxygen. That's going to be a better product. So that's really what's going to drive that through. And yeah, it looks like a bad leaving group, but consider again where it's leaving to, what it's around. Typically when we reference the negative oxygen as being a bad leaving group, it was leaving into a neutral solution. Yes, that's a problem. But if I'm leaving into a solution that is even more reactive than it, who cares? Okay? A couple of things we'll draw out. Top one, it says ether. So CH3Li or what? Like sorry, that was bad. Like either. Okay. What is the ether? Solvent. Okay. I don't really care what it is. All I know is that it's there. It's acting as a solvent to dissolve this. So not a big stress. What happens when I move the bottom one? What is that? The ACS is famous for doing this. They will throw in things like this, and you look at, oh my God, what is that? I don't know. Look at the other piece. Does the other piece show something more reactive? I have a metal, non-metal bond. That's a negative carbon. Formally negative. If I go through and look at the other piece, I'm looking at partial charges all the way through. Where's the most reactive species? The negative carbon. I don't care what that is unless I'm forced to look at it. Right? So the first thing I will do is focus on the negative charge, do the chemistry with that. Then I'll look at my answers. If somewhere in my answers I see some weird god-awful thing like that, then I'll stress about it. Don't immediately shut down on a question because you see something weird and gross. Okay? Because maybe it's there just to scare you. Okay? Which it worked. Well, actually it didn't work. You guys all got the answer right. Make sense? Okay. The lithium dialkyl, yeah, that one. Gilman. What happens this time? What do we get as a product? Okay. We end up keeping the ketone. Okay, so we will still get the nucleophilic attack on that acyl chloride because the acyl chloride is very, very electrophilic. Okay, so the dialkyl cuprate is nucleophilic. It's not nucleophilic to react with the aldehyde, or sorry, with the ketone. Okay, which means the reaction stalls and we just kind of stop there. Okay, which is kind of nice because I now have a way to modulate the reactivity. I can drop from an acid chloride to the ketone without too much effort. Kind of makes sense? And it does not react twice. Okay. Notice the yield too, 74%, pretty solid yield. Okay. Where did the other 26% go? It's an interesting question. It's more relevant for lab. We haven't directly talked about anything like that in lecture. Are those species strong nucleophiles and strong electrophiles? Yes. Okay. What happens to things is they're very strong. They start to do more reactive things to try and cancel out that reactivity. It is quite likely that you're getting all sorts of other bizarre side reactions that aren't happening in a significantly high amount, but high enough that you're losing a significant portion of your yield. It could be impurities in each of those compounds because they're so reactive that we have to stabilize them with some kind of stabilizer reagent. That stabilizer reagent could be getting in the way. Okay? So don't panic if you see lower yields. You're starting with reactive, super reactive species. That can cause issues. Okay? So there's our interconversions again. I keep having the slide show up randomly within it, so it's because it's important. You should remember it. It's not particularly relevant for what we just talked about, but it's there. Okay. So, what did we just address? We talked about our lithium aluminum hydrides. We talked about our Grignards, our cuprates. We sort of officially talked about our thionyl chloride. You should be able to recognize the water conversion. By the same token as that water conversion, you should be able to recognize the alcohol conversion out to the ester, right? Did we talk about reacting it with ammonia or any of those? Did we talk about those? No. Do we need to talk about those? Yeah? Okay. What's going to happen? Seriously, what's going to happen?
Nitrogen's going to attack carbon.
Why would the nitrogen do that?
Because it has electron pairs.
It has a pair of electrons. So it may not be the strongest nucleophile, but that's a dang strong electrophile. Right, so what happens? Break the pi bond, right? Then what happens? Kick out the chloride. We would end up with the amide. Would that be susceptible to a second ammonia attack? Why not?
Because of resonance.
Okay, so you're saying this one has resonance to make that electrophile less electrophilic. How much less electrophilic is it from the acyl chloride? What does that mean? Yeah, really. Remember that slide that I said we needed to remember? There's the amide, second from the bottom, acyl chloride's at the top. Yeah, so once we form the amide, we aren't doing anything. That's pretty much dead. Okay. What happens in, well, then the next one? Walk me through that one. What happens? Same thing? Okay. What happens in the next one? Oh, wait, same thing. Do we need to talk about those? No. You know the chemistry, okay? You have it. It's just a question of doing it. The acyl chlorides are kind of nice. We didn't talk about kind of the modulars in between there because the acyl chlorides are so reactive. They're just going to crank it out. Really, the only one that you really need to worry about would be with the Gilman reagent. That one stops, but pretty much everything else just runs straight through. Okay? And as long as you remember your order for your interconversions, once you end at one of those other functional groups, you're done. You don't have to stress anymore. Okay? Kind of makes sense? So, the textbook, I think, goes through and addresses each of those in turn. I would make the argument that you don't need each of those in turn. You know the basic mechanism. You're just doing the basic mechanism again and again and again. Make sense? Yay! So let's do the quiz again. So one thing you could go through and do with these is just predict. Say we followed the same kind of systems that we did before. So 2 carbons, 2 carbons. The next one gets a little bit tricky. I don't remember if I'm drawing this one right. I think I am. Well, last one's just ugly, so I'm not going to do with that. Gray up, I'll draw it. Fine. Twist my arm. Okay. So I would make an argument 1, 2, 3. 1, 2, 3 are all going to be particularly relevant. 4 becomes relevant if we draw the other piece. And for those of you panicking, I'm not saying those are the answers. We're starting with the carboxylic acid in the first one, and we're ending with an ester. It's not the easiest transition to go through and make under pretty much any circumstance. Okay? The probably most relevant piece to address would be the carboxylic acid in the presence of a base. So more than likely what's going to happen is you'll end up deprotonating that and get the negative charge, which then means we don't get a very easy transition across to the ester. As it was, the carboxylic acid and the ester are on an equal rung at best. Okay? So that's not very likely to happen. More than likely, you're just going to get the acid-base reaction, and we won't see the conversion across to the ester. If we move to the next one, we have the anhydride. And between the next two, we have either the carboxylic acid or the amide. Did I become more stable or less stable going from an anhydride to the acid or amide? So because we've seen that slide so often on our rungs, we would know that the anhydride is the second from the top, the amide is the second from the bottom, and the carboxylic acid is pretty much in the middle. So we've gone down in energy. Is that a favorable thing to do? Yeah, that reaction is legitimate. That's probably going to happen. Right? Bottom one. We're again starting with an anhydride. Second from the top, very likely to go through and happen. I didn't spell that right, but that's close enough. Carboxylic acid. And carboxylic acid is lower on our rung, and officially it wouldn't even be the acid. It would be the carboxylate, right? Pretty much on the bottom. That's not a big deal, except what's the last one? This is officially an acyl bromide. Where's the acyl bromide? The tippy-tip top of our activity. Right? So I'm starting with something reactive, and I'm trying to end with something even more reactive. Not going to happen. That reaction is a no-go. We're not going to see anything. That's probably a no reaction. Make sense? Upper right-hand corner, the focus in the upper right-hand corner is making the amine. That's why I drew that first and why I boxed that in. Okay? The unfortunate thing within this reaction is that's not the part that helps us decide that this reaction is valid and this is what's carrying through. The part that, whoops, where did I draw that? The part that's carrying this through is that we end up with the carboxylate versus the amide. The carboxylate is the bottom rung on our activity. So I'm going from an amide to the carboxylate. That makes sense. That's moving down my system. Okay, so that is a valid reaction. That one's extra tricky because, again, we focus on the amine part, which in most of our other reactions, it's whatever the leaving group is, and we're like, yeah, whatever, I don't care. But the leaving group is the important part for this reaction, okay? Not the carboxylate part. Okay? Last one, lithium aluminum hydride supplies our hydride again, strong nucleophile. We know that should attack our ketone. Okay? The harder part is what it should do with the amide. Okay? Yes, it should go through and attack the amide. It's lithium aluminum hydride. It's going to react with our amides. Okay? After it, or when it does that, the result is we would end up with something along those lines. Okay? That functional group, as we've got drawn on the board, is very, very similar to what is effectively a hemiacetal. And what do are hemiacetals stable? No, they revert back to their polar pi bond state, okay, by ejecting a leaving group. Okay? In the hemiacetal system, it wasn't a big deal because we were kicking out oxygen. We're like, I don't really care. It's the same thing. It's oxygen. In this case, it's slightly different because it's now oxygen versus nitrogen. Which one would be a better leaving group? Oxygen, because electronegativity. So we're evaluating the charge of that leaving group. Okay? The oxygen can deprotonate our nitrogen or remove a hydrogen from somewhere in solution, okay, become an OH, and it would leave as hydroxide. Hydroxide is a less active base than the amide. It makes sense to kick out the hydroxide. The result of that move would then be the imine, the carbonyl equivalent for a nitrogen. That's a polar pi bond. What does the lithium aluminum hydride do? React with polar bipons. So there's a polar bipond, react with it a second time, and you end up with your final structure. Okay, assuming I didn't lose carbons in that. I think I did it right. Make sense? Okay. Yay, sort of new stuff. Officially not sort of new stuff, because we've also talked about this one. Br2 in the presence of PCl3 and H2O. Interesting result. We get, fascinatingly enough, a 95% yield with the bromine being located there, right? So what kind of reaction happened? Right? We just look beginning to end, this looks like a substitution reaction, where I substituted what for what? Hydrogen for bromine. Okay? It's kind of neat because we got rid of a hydrogen, so no reactivity virtually for a bromine. So that's kind of cool. Okay? That means that our hydrogen, one of those two, had to be what? Acidic. Okay? Are they acidic? This is a harder question. If you say yes, why? Okay. We've got a carbonyl, right? We're looking at the alpha position to that carbonyl. Alpha hydrogens, two carbonyls, are acidic. Okay? Why are they acidic? Resonance. If I remove that hydrogen, I would have a negative charge. That negative charge can do resonance with the carbonyl. Okay. So that makes sense. However, carboxylic acids do not have acidic alpha hydrogens. Why do they not have acidic alpha hydrogens?
Because the hydrogen on the oxygen is the most acidic.
Because they have more acidic hydrogens on the outside. That's why they're called carboxylic acids. Right? It is the acidity of that. If I removed that hydrogen first, I would then have a negative charge on that oxygen. That's not stable, so what does that negative charge do? Sort of. Does resonance into our carbonyl, effectively making the carbonyl what? Less electrophilic, less positive, meaning that negative charge less likely to form. Okay? So if I start with a carboxylic acid, I can't do a nice substitution reaction that I would have done with the ketones or aldehydes. Okay? And yet somehow if I look beginning to end, doesn't that appear to be exactly what happened? Okay? We've got the bromine, that makes sense, using our alpha hydrogens, all of that seems to make sense, except PCl3 doesn't really make sense. Why is PCl3 there? Well, what did PCl3 do? Any place we have an OH, it gets replaced with a bromine. You're right, fair enough. PCl. Chloride. Okay. Now what happens? Why are the hydrogens now acidic?
Because you don't have the more acidic hydrogen now.
We've lost the more acidic hydrogen on the carboxylic acid. Good point. And
We made the carbon more electrophilic.
the carbon is now actually more positive because we don't have the resonance effect from the chloride stabilizing in. It can't do that resonance effect, not at least as well. Which then means the carbon is more positive. That makes those hydrogens more acidic, more susceptible to removal, and I can actually make that my nucleophilic carbon. The nucleophilic carbon can then react with the bromine. Awesome, I do my full substitution, and that would put that bromine at the alpha position. But that's not what I end with. I end with the carboxylic acid. Well, what happened?
Added water.
In step 2, I add H2O. The acyl chloride is a stupid strong electrophile. Water, being a weak nucleophile, can come in and attack. We do our nucleophilic addition and elimination as normal, and we get right back to our carboxylic acid where we started with. Right? So it's kind of this weird, bizarre reaction because we end up doing something that appears to be relatively simple and straightforward, but would not work under normal conditions. Okay? Because it didn't work under normal alpha hydrogen conditions, and now magically, because I've added in this new reagent that somehow did some chemistry that isn't apparent at the beginning, okay, we attach a name to it. And that's the Hell-Volhard-Zielinski reaction, which, for no other reason than it's fun to say, is why I would say it. Okay? Kind of makes sense? So focus on the chemistry, see what happens, address those pieces, and just kind of move your way through. Okay. This goes through and addresses it in a little bit more detail. Right. Next section are sulfonyl chlorides. Have we talked about these before? Yeah, we did. Okay, we did talk about that last one, the tosyl chloride. Back in chapter 10, when we were trying to make an oxygen a better leaving group, we reacted it with tosyl chloride because the sulfur was a phenomenal electrophile. The oxygen was willing to attack it. Why was that sulfur a good electrophile? We have an inductive effect. 3 electronegative elements. Okay? We have a resonance effect, making the sulfur positive. We have a great leaving group in the chlorine. Okay? The mechanism behind that was that our alcohol had its electrons attack the sulfur. What then happened? We broke a pi bond, right? You mean we did a nucleophilic addition to a sulfur compound? Yes. Those pi electrons came back down, reformed the pi bond. We exceeded the octet, we kicked out the chlorine. You mean we did a nucleophilic elimination? Yes. Yes, we do. That is exactly what happened. Right? So when we talked about it back then, I said the mechanism isn't that big a deal. You have to remember that this is what it does. Right? Here's the mechanism. If we go through and take a look at the other ones that they've got listed up here, okay, triflunyl chloride, what is common between it and the tosyl chloride? Not to give too many hints away. What is common between those 3 reagents? We have that sulfur with 2 pi bond oxygens and chlorine as a leaving group. All we're changing is modulating the R group on these. Depending on what we're trying to do, we may vary those for differing reasons. Okay? The triflunyl ends up being one used as a protecting group because we can undo that one. I believe that's one we can undo. Okay? So depending on what we want to do, we may use a variety of these. Okay? But the chemistry is still the same. We still have that sulfur. Don't stress about the R group. These are all doing the exact same thing. Kind of make sense? Okay. We have the mechanism drawn neatly kind of underneath. Yippee. Okay. So, more fun with predicting. Yep, your turn. We got 5 reactions. I'd like to see that. Okay. So, unless there's any arguments, I'm not going to draw the first one, because I think you guys got it. I did see people drawing out mechanisms, which is kind of nice. Okay, to draw out the mechanisms, that can help out. And that's partly what's going to explain what's happening up here with the 2 equivalents. So if we take a look at that second one, I've got 2 sets of arrows, red or blue. Which arrow set do you think makes more sense, red or blue? So I've got to vote for red. With the 40 people we have in this room, we should get a little bit more than 1 vote. You say red, 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 red. Everybody says red. I would bet blue. Why blue? Or why red? Try that. What's the result if red comes out? Right? What's the result if blue comes out? We wouldn't get the same thing. We get H2O, right? Yes, we'd get the same thing going backwards. True. Yeah. So why is blue make more sense than red? Or why does red make more sense than blue? Both of them make sense. Nice kind of couched term there. Let's do better than that. They're both good leaving groups. Yes. Is one better than the other, and why? Remember our rankings on how we establish pretty much everything we do. We start with charge. Water isn't charged. Water's probably the better leaving group. It's iffy. I think their leaving group ability is pretty darn close between the chloride and the water. Chlorine is just that much larger that it can stabilize that negative pretty well. Okay? So let's make sure it's not iffy. How could we go through to change our mechanism so that we don't have to worry about that iffy situation? Don't eliminate yet. And I would go through and erase, but everything's so small I can't get in there and erase cleanly, so I'm just going to have to show another set of arrows, which I have chemistry instructors that would flip their lids at this already, but we're just going to deal with it. So instead of fixing the negative, which I agree, you want to fix the negative, we just can't fix it yet because that doesn't show as large a favoring for our final products. So let's not fix the negative. What should we fix? How do we fix the positive? Have water that's floating around still in solution pick up that hydrogen. Now if we go through and initiate our red-blue, can I erase the hydrogen? Are you guys okay with that? Okay. Now if we went through and made the argument between the red and the blue, our red would be Cl minus and our blue would be OH minus. Now which one's the better leaving group? Cl minus, hands down, you're absolutely right. There's no question. Okay. So a subtle change in your mechanism can result in pretty drastically different kind of end results or end conclusions. Okay. The biggest issue that I would argue with this that comes up isn't so much right there as being the problem, or comparing chloride to water as leaving groups, but that if you did the chloride without removing that hydrogen first, your product after that elimination becomes this, which is the conjugate acid of carboxylic acid. So we are having the more acidic version of a structure that is already acidic. Yeah, that's probably not going to happen. Okay. That structure is now astronomically high in energy. We want to deal with that hydrogen first and then deal with the chloride. Okay. Just to be a cleaner mechanistic step. Everybody was making the mistake as far as I saw, so there's not singling anybody out on that. You're just following through the patterns that you're used to doing, just getting to that answer, which is good. Now think a little bit more carefully about your mechanistic steps to be like, actually that didn't make as much sense. Make sense? Okay. Bottom one, there was a little bit of struggling with that, but I think we're okay with that bottom one. Bottom left. Yeah. Why two equivalents? So I saw a couple people really stumble out on this one. Well, what product do we get? Should I actually try and cram this in here? This may be a bad idea. There's 9 carbons. Right? Everybody get that as an answer? Or at least got there and we're like, what the hell do I do with the second equivalent? Okay? Well, what do you do with that second equivalent? Rewind a step backwards. You probably were here. How did you remove that hydrogen? Something basic in solution. What's the something basic in solution? The second equivalent of the amine. Okay? So when we do these amide formations, we usually need 2 equivalents of the amine because one of the amines gets killed pretty quickly, okay, by removing the hydrogen in this intermediate structure. Pretty much the exact same statement that we made back with that second one, with the water. We formed that superacid effectively. Okay? And we don't want that. So how come in that question we didn't say 2 equivalents of water? If it makes you feel better, I'm just guessing at this. I would make the argument the amine is probably also your solvent. Okay, it's possible the amine isn't your solvent. Okay, and we could be using some kind of polar acetone. We could use acetone. We could use something like acetone to dissolve it, and that wouldn't get in the way. Okay, so that is possible. Since water's the solvent, we don't have to specify the equivalence because the solvent is there in a vast excess. Okay, so that probably contributes to it, but there is no statement as to the solvent in the amine one, right? We're just making the guess that there probably was a solvent and it wasn't water. Because if it was water, it screws the reaction up, right? Okay. So it had to be a non-nucleophilic, probably polar solvent like acetone. Other ideas? I think it's going to come down to water's everywhere kind of dilemma or statement. Okay? Water is everywhere, meaning it is stupidly cheap. The amine, not quite everywhere, which means it's expensive. Amines are also pretty toxic. They usually tend to kill most wildlife, okay, or fish wildlife. Okay? So we want to limit the amount of amine present. If we're going to limit the amount of amine present, we have to make sure we have enough to get the reaction to go all the way through to completion. That's why we need the 2 equivalents. Water being so cheap, we probably dumped in there in tons of excess anyway because we're like, whatever, it's water. Okay, I could spit in my reaction and it would work well enough. I don't even have to use like clean water. Okay, kind of makes sense? So really we need the 2 equivalents at least for water, but being a solvent and being in vast abundance, probably why we don't specify the amounts for water. It's non-toxic. The amine is toxic. We're going to limit its presence, okay? Which is probably why it won't be a full solvent. Okay? Last one just happened to hit me while looking at it. This last one actually looks like a biochemically relevant molecule. But you should end up with something like this. The biochemical relevance Those of you that had me for first semester might know this. Colton, you might see if you remember this from your classes. I'd be surprised if they talked about it, but maybe they did. What did I just highlight? Isoprene units. Isoprene is your basic building block for nearly all biochemical pathways. Okay. Steroids, hormones, all of them are isoprene units, or a sequence of isoprene units. So I don't remember the context of where I stole this from the book, but it's probably associated with that. So we end up converting an ester to an ester. Is that going to be particularly stable or thermodynamically favorable? No, we're just going side to side on our ladder. Okay? So we may not have a huge equilibrium favoring one way or another, but I can do the conversion. And because there isn't a huge favoring one way or another, what might I do to help force the reaction one direction or the other? Put a lot of one of my reactants in there to up it according to Le Chatelier's principle, or try to remove product as it's formed. The removal of products as they're formed is going to be challenging because we have an ester and we started with an ester, which means their intermolecular forces are virtually identical, which means their physical properties are virtually identical. We're not going to separate nicely. Okay? Same for the alcohol. You'd be looking at isopropyl versus methanol. That's not going to be easy to separate. So to force this one to our products, we're really probably just going to have to put in a ton of our starting material, of one of our starting materials, which then begs the question, which starting material should I put in? Blue or red?
Red.
Why red?
Because we want to react all the blue.
We could say react all the blue, that's a possibility, but we could just keep cycling the reaction over and over. So I don't quite accept that answer. I mean, that's probably a better answer than mine. Let's go through and say that.
There's a lot of blue and just more likely to go side to side, go a little cheesy.
No, as long as we have a vast excess of one of our reagents, it will favor products. Which car are you going to buy? The really, really big car or the really, really small car? Which one can you afford? Neither. Probably go with the smaller one, right? Because the really small car is cheaper. Okay? Between those two reagents, which one is smaller? The red one. Guess what's likely going to be the deciding factor on this? Cost. Methanol is going to be significantly cheaper than that ester. We're probably going to dump in tons of methanol to try and push this equilibrium based pretty much solely on a cost analysis. Okay? That last reaction, we started with an ester and ended with an ester. Okay? So that process means we converted between esters. Okay? So we did a trans esterification. So that's what this slide is saying. We'll get some names for these nucleophilic addition and elimination reactions. One of them is a trans esterification, okay, because you've started with an ester and became a different ester. So it's just a I keep saying the same thing. It's called a trans esterification. The bottom one is a saponification, which I don't think I had listed up there. Okay, but we start with an ester and we end with a carboxylic acid. Why would we call that a saponification? Anybody seen this symbol before, written in like English text? It's usually not around letters, it's usually around words. It means you need to do a word swap when you're typing up, like you accidentally your just sequence of words was out of order, okay? And you just need to swap those words around. Okay, what happens if we do that here? I need to swap the O. That's a word, isn't it? Soap. Guess how you make soap? Really, no one wants to venture that. It's a saponification reaction, is how you make soap. It's the conversion of an ester into a carboxylic acid. Carboxylic acids are soap, okay, or can be made into soaps. So that when you're using soap, it is, at its heart, a carboxylic acid structure, okay? If you go through and run that reaction, it is known as a saponification. Okay? The most famous saponification is converting lard, okay, which is an ester. Triglycerides are esters, and converting them into their acid form using, usually, potassium hydroxide. Okay, so you can go out to the store, buy a bunch of lard, buy a bunch of potassium hydroxide, mix them all together in a crock pot. If you haven't heard about this, you can do it. It's not that bad. You just make sure you know the ratios, otherwise you end up with soap that like melts your face. So you do have to be a little bit careful with the ratios. But you find a source that you trust the ratios on. And then mix it all together, stir it around for a little bit, let it harden, and then you can cut it out of the crock pot, and you have soap. So, neat little process. If after doing the KOH, you decided to then add it to acid, you protonate and you'd end up with the carboxylic acid form. Okay? But the soap form is the carboxylate. Why would the carboxylate be the soap form? What charge do you see out there? Negative, which would mean that part of the structure should be polar. What should it do in water? Should dissolve in water. Does soap dissolve in water? Yes, that's why we use it, right? What's the other reason we use it?
It has a non-polar.
It dissolves all the dirt. Dirt and grease tend to be nonpolar. So when we're looking at soap, it usually has a long nonpolar tail and a polar head. The nonpolar part can be used to dissolve our dirt. The polar part can be used to get it to dissolve in water. That's where it comes from. Saponification. Yay, done.